Hello everyone, CJ Peaceful, and I wanted to do a quick video and give you an update to my plate gap theory. And the reason why I'm doing this now is I've been really thinking about the last video I posted and the results I posted, and here they are in front of me. You can see them again. This is regarding this 9-plate cell. In earlier videos you'll notice that this wasn't completely enclosed in acrylic, and the reason why I didn't enclose this side is because, well, it leads me to why I'm posting this video. Like I said in previous videos, this cell probably looked a little different, specifically the spacing between the plates. I had the same number of plates, but the spacing was much tighter. In fact, it was half the width. The spacing was typically half the width of what it currently is now. What I have now is two 1/16 of an inch nylon washers. In the previous videos I was using just one nylon washer, which gave me a 1/16 of an inch gap between each plate. Now, really had some time to think and really ponder about the results that I posted the other night about the previous cell configuration using the 1/16 of an inch spacing. And as I stated in the video, that cell, or that design, was rather constructed using what was at the time the equation I had constructed regarding my plate gap theory. And up until recently, I was almost sure, I was almost 100% sure that in order to see or get consistent results, you had to deal with the number of volts you were designing your cell specifically for, and didn't really take into consideration amperage. So what I've done here is look back at that equation and really thought, I sort of came up with the conclusion that it's not necessarily the voltage per se that affects production in brute force electrolysis. It's more of the amount of current passing through the cell. Now, before those of you who feel that voltage is more important, if you will, than amperage, I'm not saying that voltage is not necessary. As previously stated, they go hand in hand. You can't have one without the other. And that was just something I completely overlooked. So what I've done is went back and redefined some of the parameters in my equation. And what you'll notice is here, this top line. I've changed this from the previous voltage, target voltage, to the target amperage, if you will. And that makes much more sense in dealing with this type of cell construction using plates. Everything else I believe is the same here. I may have stated a little bit differently with this revision, but my intentions are to be the same, or taken the same way. I've had a few questions about this 1.23 volts. Clearly, if you do the research, it's been stated many times over and over again that if you were to use distilled water, or the purest water you can possibly find. In order for electrolysis of water to occur, the minimum voltage required to create or to initiate the chemical reaction is 1.2 volts DC direct current. And so I went ahead and just rephrased this. I've seen other numbers on the internet, anything between 1.23 to 1.5 and as low as 0.7. And some of them make sense, and I think a lot of it has to do with the purity of the water. And I think some people take into consideration the electrical potential of the water, meaning that they're possibly take into account an electrolyte in the water, which will change obviously the required voltage. Actually make it lower, I believe. But anyway, the rest of this of course stays the same. I feel that you still need to accommodate for your thermal current cycling through the cell, and in order to produce an efficient cell, you definitely have to take that into consideration. And I think right here, this last paragraph clearly states that, and it's the same as my previous statements, saying that basically if your cell vertically, say is more than 2.5 times or more than say the width of the cell, then you must factor in for that height difference. And so what I've done is typically I multiply Z, which is my output, by 1.5. Now, I've said this before, and I'll continue to say this. This theory that I have is a work in progress. By no means do I mean to represent it as law. I am not a scientist by profession, and I know the realities of pursuing such a task. And I think, though, it's a good base, a good starting point for one to begin constructing a plate cell and producing an efficient cell. If you have not seen my previous videos, I highly encourage you to at least listen to the audio if you do not want to see the video, because I know I have a tendency to focus in on an object and just randomly blurb, and I apologize for that, but I think a lot of this will make more sense if you review my previous videos. I think you get a better understanding of where I'm coming from. But anyway, I'm going to rerun this cell using my revised equation. And what I've done is I punched in some numbers with the idea of seeing no more than a maximum of 20 amps across this cell. Now, this cell I'm sure can handle much more, and if you take the notion that quarter of an amp per square inch of surface area is acceptable, at least a maximum, then this cell, I believe, when I calculated it out, came to 36 amps. But that's much more than I would like to see. So, based on input of 20 amps and the desired spacing and the number of plates, this is what I've come up with.